Okay, this is example 458. It says if the tension in the cable is 140 pounds, determine the magnitude of the moment produced by this force about the hinged axis CD of the panel. Okay, so once again, we are going to use the scalar product. So if you remember from class, in order to calculate that, we're going to need the moment of F around CD. That's going to equal the triple scalar product, which looks like this. So what do we need? Well, first of all, just to remind you, this is a unit vector representing the axis of interest. So this would be UCD. So now I'm just going to put the CD there. F, of course, is just the force vector. And R, this would be a position vector from any point on the axis of interest to any point on the line of action of the force. Okay, so this actually opens up a bunch of possibilities for us because there's two really identifiable points on the axis of interest, particularly C and D. But also notice there's two pretty good, well-defined points, A and B, on our line of action of the force. So honestly, what you could do here is you could use C to A, or C to B, or D to A, or D to B. There's four possible ones you could use. Because as long as you start with a point on your axis of interest along C to D, to any point on your line of action of the force, A or B, that gives you four combinations to work out. Now, I will be honest, there's usually one that's easier to work with than all the others. So notice if you're looking at these, I won't show all of them, but I mean, just sort of looking at it, I would say that C to A is probably the best way to go, probably the easiest. Like, for instance, notice for C to A here, that's just going to be 6 I hat feet. So let's use this one, and I'm going to call it C to A up there. Okay, so we have one of the vectors we need. The other things we need to do are to figure out the other quantities. So for the line of the axis of interest, the axis of interest is basically we need to find, sorry about that. We need to find a vector that points from C to D and divide it by its magnitude. So notice for C to D, that is just going to be 0 I hat plus 8 j hat plus 6 k hat feet. And the overall magnitude of that, by the way, is if you do 8 squared plus 6 squared and take the square root, it is going to be 10 feet. And the feet cancel here like this. So this UCD is basically 0I plus 0.8 j plus 0.6 k hat. That's one other thing we need. And the last vector we need is the force. So with the force, what we need to do is we need to find capital F here, where we multiply its magnitude, which is in this case 140 pounds, by the unit vector that points from A to B. You can see that we are going to go -6 I hat plus 4 j hat plus 12 k hat feet. And the overall magnitude of that, if you square each component, add them together, and take the square root, this gives you 14 feet. So F is going to be 140 pounds. This is going to be -6/7 plus, 6/14 plus 4/14 j plus 12/14 k hat, which turns out to be -60 I hat plus 40 j hat plus 120 k hat pounds. So if we now do our scalar product around axis CD, we're going to use this. And we can set up a matrix where the first row is that unit vector representing the axis of interest. So that's 0 plus 0.8 plus 0.6. The next line is RCA, which we're going to use as 6 I hat, 0J, 0K. And then minus the force minus 60, 40, 120. And now I can evaluate it. So this is going to be 0. Basically 0 times 120, take away 0 times 0 times 40. The whole thing's going to be 0 anyways. Minus, so 0.8. This is going to be 6 times 120 minus 0 times negative 60. And then plus 0.6, 6 times 40 minus 0 minus 60. And when you add all this up, you get it to be minus 432 pound-feet. But they asked us for the magnitude of the moment. The magnitude is 432 pound-feet. The minus sign just means what it would be going clockwise. The direction would be clockwise around axis CD. All right. That's that question. If you have any questions about it, please get in contact with me. Other than that, have a great day. I'll talk to you soon.